Hello, AP Statistics. I hope you guys are doing well on day, I think we're at 14 of quarantine school. Um, so I'm here reporting live from the CDC in Atlanta, where currently lots of research is happening, lots of data is being gathered, decisions are being made as they research this virus. So let's look at some of the key features of what's going on as they gather that data and make those decisions. So this is chapter 7 in our Five Steps to a Five book. This is designing studies, sampling surveys, and experiments. How do we gather data? This is the chapter that doesn't do math, basically, right? It's vocab. So, you want to be up with your vocab. This is one of those things where, like, yeah, the more you can know, the better. But this might also be one of those good chapters. Now that this AP test is all open note, this might be one of those good chapters to flag. Like, hey, samples, all those sampling methods, I kind of get those confused. I get the simple random sample mixed up with the systematic, mixed up with the stratified. Just put a little like sticky note on this page, or do something, or make a note, a sheet like, oh, page 118 is my sampling methods, because this AP test is now open note, and so you can have this book with you when you test, among other things, right? There are other resources you can make use of, but that's I think making this kind of going through and highlighting and making notes, and maybe putting little stickies on pages or something, little tabs, or just notes of what pages are where. I think could help a lot in on the day of the test. You don't want to rely too heavily on that because the AP test is short, right? It's 45 minutes, 2 questions. You're not going to have a lot of time to be reading big old blocks of text. But if you real quick need to come here and just check, oh wait, which one was stratified versus cluster, and you want to read that sentence or two, like that would probably be fine for AP testing purposes. All right, but yeah, it's all about gathering data. So first of all, we want to get samples. All right, that's our both surveys, observational studies, and experiments. Ideally, we get representative samples. Experiments, a lot of times we end up with volunteers, so some of this stuff doesn't happen there, and so we've got some downside where we can't necessarily generalize those results, but we really want a representative sample, right? So the census would be nice, but it's not a reality, right? We can't get information from every single person in our population. If right now we're interested in the individuals infected with COVID, then we can't do a census. It's too hard to reach everyone. But we want to draw conclusions about everyone who contracts the disease. So we get ideally a representative sample if we can, to study that, right? We don't want all people from one location, or all old people, or all young people, or whatever. We want a representative sample. So we want to avoid bias. Bias comes from the method. If our method favors it, it's not just chance variation. So when you get your sample, it might be off, right? It might not be representative, even though you did good random sampling methods. So that's something we can't really control. That's not bias. If our sample just happens to have too many old people, or too many young people, or too many of this or that, if we did a nice random sampling method, that's not bias. Bias is if we have, and there's a number of ways we'll look at where it can come up, but if our method favors a particular outcome, that's when we're talking about bias here. So we try and use probability samples that we ultimately use chance to make that decision. All right, so we could find the probability of all of those sampling frames, like all the possible people we could select from. So of our probability sampling, these are generally our good sampling methods. Our simplest, or sorry, I guess random sample is also a kind of a general term where every member of the population is equally likely to be included. So that the thing about that is like the simple random sample is included in that, and the stratified random sample is in that, right? Where if you do it right, everybody has an equal chance. A cluster sample, if you do it right, everybody can have an equally likely chance. Systematic, everybody can have an equally likely chance. So the random sample kind of covers all of those if they're done properly. So within those, the one that we use the most is the simple random sample, where we just take the entire population of people and we get a subset from them randomly, right? Ideally, our sampling frame, that entire population, we have a list of everybody, and we can just choose some number, and you could use a random number generator labeling. Sometimes you have to describe this process. You have to describe how you would label individuals, how you would generate the random numbers. Important to note, a lot of times that you would not use replacement when you're describing your random sampling method. Get your individuals, they become your sample. So that's a lot of times our statistics really are based on that. But there are a couple other methods that work pretty well. The two, systematic and cluster, are both actually a little bit lazier. Generally not quite as good actually as just a pure simple random sample. The systematic is where you choose, like, the individuals are in some sort of pattern, they're in a row, or they're, you can kind of go down the line or down the phone book or what have you, and you get every 10th person or 100th person or every 50th person, whatever. You pick some number. You randomly pick within the first 50, but then you go every 50th person after that or something like that. That's systematic. So it saves you a little bit of that trouble of just like totally finding all these random numbers that you generate from your simple random sample, but it's still pretty good as long as there's no pattern to the individuals. The cluster sample, also a little bit lazier. You usually take those in entire groups. If they're already grouped together, you might survey everybody on a particular block or everybody in a particular hospital, right? We might just randomly select, 50 hospitals out throughout the country and pick all of the COVID patients from those or something like that. Stratified is actually a bit more work and an effort to make it a bit better. Right? So we want to make sure we know there's some variable that we think might be related to our response variable that we're going to be studying. In that case, we make sure we get some of each group. If we think different age groups are going to be related to that variable, we make sure we get some from each strata. We kind of make these strata up, but they're based on pre-existing features of these individuals. We don't assign the strata. It's something that exists about those people. Maybe I just want to make sure I get boys and girls in my sample. And so I make sure I get, and usually you want to get representative samples, right? I want to get half boys and half girls, but if there's some other thing we stratify by, we want to make it representative. We want to get a proportion in our sample that matches that proportion from the population. And that kind of actually reduces a little bit of the randomness, but it's in an effort to control for that chance variation, kind of get us a more precise representative sample in the end. Got some examples there you can check out. And then bad sampling, all right? So we've got self-selected or voluntary response. That can lead to bias. Generally, people who feel really strongly, or just the people who you reach, that can lead to a lot of bad results. Convenient sampling, just kind of similar in gathering data, not in a quick way that's easy, just kind of standing out on the corner or whatever, gathering data from just wherever it is easy to get it from, can also lead to bias, lead to favoring particular outcomes, one or another. This is one that we had not. This is not in our textbook, so I want to mention it now. I haven't seen this on the AP test before, but it's an interesting one. Quota sampling. So it's kind of actually like stratified sampling, but it's not random. So you try and get, like, it's a person who's doing the poll actually attempts to get a representative sample. They like, I want an old person, I want a boy, a girl, and they try and actually be a little more strict about it, not just entirely convenient, but they still do just kind of make their selections. They're not actually using randomness, right? So it's probably better than these, but it still can be subject to bias and for a number of reasons we may or may not be able to know about. So yeah, that leads us right into bias. So again, it's kind of relative to your system. If we produce estimates that are on average too high or too low, we favor a particular outcome over and over again. It's not just one sample that's too high. If I use a random sampling method, a simple random sample, and the result is high, that's not bias. That's just chance, a high sample, right? It's not necessarily representative, but it wasn't bias. Bias is if we repeat this process over and over and over again, it tends to favor a particular outcome. More often than not, we get higher results than we should. Then that's bias. And so that can result from the sampling method. That can also result from things like undercoverage, which can come from these things. Undercoverage can come if our sampling frame is incomplete, we don't reach a certain type of people, that even if we're using random sampling methods, we can end up with undercoverage. We have non-response can lead to undercoverage, right, where certain people choose not to respond. So you kind of have undercoverage, and really you can have overcoverage as well. A certain type of person tends to respond, right? You might have too many people that feel strongly, or old people or something that volunteer to participate or what have you. So those types of things can happen. Yeah, voluntary response, the people who choose to respond a lot of times aren't representative of your typical people for one reason or another. It's hard to get busy people, working people, things like that are easily lead to under coverage, and are often lead to non-response. They choose, you contact them. Non-response is when you actually contact the person and they choose not to participate in the study. We can have wording bias if you're asking questions, right? You'd rather measure, if you can, right? You get a better result if you measure somebody's weight than ask them what their weight is, right? You're actually going to get a more accurate result if you can measure something. Not everything can be measured, though, so sometimes you have to ask people questions, in which case then people don't answer honestly always. Sometimes not even unknowingly they answer dishonestly, and you might lead them. The question might be leading in a particular way, and you want to keep the questions simple. You don't want to like present facts and they say, do you agree with, these scientists who all say this? They don't want to put any pressure on them. Like if you really want their opinion, just ask the question, simple, plain, and ideally it wouldn't be something that like they're going to feel pressure to lie about. So yeah, that's the wording of the question can lead to that. Depending on how you ask the question can affect those results. Response bias arises from a number of ways, and I would say wording of the question kind of is a little bit of a response bias. It's they're responding, but it's biased towards a particular way because of the type of the question that you're asking or who's doing the questioning. That can lead to those response biases. All right, so that's pretty much it they have in here for sampling and serving. Then experiments versus observational studies. So ultimately, they kind of mention this idea of statistical significance. We get to this much later, but I'll go ahead and mention it now. Statistically significant is when that difference is too large to attribute to chance. That's what we want to know, right? We want to see that when we try this new drug, for a disease, is it statistically significant? Is that difference, that people get better, or are they getting, less likely to get the disease? Is that difference significant? Because if you just choose two random samples with, you give two different placebos to two groups, you'll actually get different results from those, right? If you give them even the exact same treatment, you won't get the exact same numbers. One group might be a little bit higher than the other just because of your random sampling or your randomization and experimental design. So we need to see statistically significant results that difference is so far that it wouldn't just be chance sampling, and that's somewhere all that math comes in later on, and we'll get to that. But so ultimately, we want to do that. If we want to establish cause effect, we want to do an experiment. So we're imposing treatments onto our experimental units, which is or we call them subjects sometimes if they're humans, but or individuals is another term we have for those. But we impose treatments, and then we look at that response variable. We're not just observing, right? That's the idea. Observational study, you just observe, right? You have this, you collect data, you just observe, but you're not imposing a treatment. So you might notice relationships, you might see a correlation between variables, or you might notice that one proportion is higher or something like that, but you can't establish cause effect unless you are doing all those elements of experimental design, keeping variables the same while tweaking some, and then seeing what those responses are. So got those, and that usually shows up. So I'm interested to see how once I get some more information about this AP test. There's almost always like one question on the AP test from this chapter. There's almost always one question from the descriptive statistics. There's almost always one that deals with bivariate data. There's almost always one that deals with, you're going to do a state plan to conclude. There's always one that has probability random variables. So I don't know. I imagine that what we're going to see is they're going to kind of compact these into one question, right? They're going to have something where they describe some, I assume that there's two questions. There's a 25-minute question and a 15-minute question. I assume in the 25-minute questions they're going to pack like three of those in there, right? You're going to have like, oh, here's their study design. What do you think of this? Or what, something like that. You're going to have to analyze that, and then then here's their descriptive statistics. Describe that, and then they're probably going to have all three parts in one question. So eventually, I'm going to get you to practicing some of those. They've had those in the past where they combine two or more topics together. I'm going to have you do a lot of those at the end because I assume that's what's going to be going on with those questions. And then there is no like question 6. There's no weird going in a different direction. I don't have time for that this year. So I guess good news for you guys. So I imagine there'll be something in here. They really like to do something on experimental design where you describe it. And it can't be super in depth, but they'll at least I imagine make you do a little something with this. All right, so then with experimentation and observational studies, we have the idea of confounding variables, variables that are related to the effect, the response, but we can't necessarily separate them from the treatment. So we try and control for confounding variables, and that's something that can exist in observational studies. You might see, oh, well, this variable is tied to that variable. They're related. Well, it could be that there's some third confounding variable that's kind of mixed up with both of them, and it's hard to tell how much is it that they were taught well versus their parents, gave them good DNA versus their parents gave them good study habits. All those variables are confounded and mixed up. It's hard to tell, which one is actually causing the effect. So that's that. So we try and, when we're doing experiments, we try and use statistical control. We try and hold constant every variable we can. We can't necessarily do it all. That might have an influence on the outcome. So we try and keep all of those the same as best we can. And then the other thing we do is to kind of control for those confounding variables is we actually do randomization. So yeah, and these are the three principles of an experiment. We need control, we need randomization, we need replication. But randomization kind of actually is another control. It kind of controls for the things we don't foresee, like the variables we don't even think to control or can't control. Ideally, randomization keeps the groups about the same across all the variables, even the ones we're not thinking about. That those two groups are about the same. They get the same split of all the different things, that the variables that could be related. And then replication. So in statistics, replication, this is often confused with scientific replication. Statistical replication is just do it on enough units. Get a big sample size. That's what we mean with replication. Don't just do it on 1 or 2 or 3. It's not just anecdotal. There's a few cases. It needs to be lots of replication to reduce that sampling variability so we can make good decisions. Sometimes in science, they refer to this replication as the idea of repeating the entire study, repeating the experiment. And that is a good process to do, to make sure that, if we can do it here, that in Europe they can get the same results. Otherwise, there's something we missed or they missed or something. But that's not what we're talking about. That's not scientific replication where you do the study again. It's just do it once. Statistics doesn't think you should do it multiple times, though. You should just do it once with one big sample. And so that's the idea for designing an experiment. So your simplest design is a completely randomized design. You take your individuals. Ideally, they would be a simple random sample, but that can't always be the case. If they're a simple random sample, that's probably representative of the population. If that's not the case, you might end up with volunteers. Your volunteers for something like studying treatments for this COVID disease, like you might end up with healthier volunteers, right? People who are younger, people who aren't at risk. So we can draw conclusions for people similar to those in the study. And a lot of times you should mention that if you're dealing with volunteers for a sample. Like, we can really only draw conclusions about people similar to those that volunteered. We can establish a cause-effect relationship for that group, but we can't necessarily be sure that it happens for all groups, the older people, the other at-risk populations, and so on. And so a lot of times research lags behind for those at-risk populations because we don't just let them volunteer right away, right? We're not giving new drug treatments to old people, pregnant women, babies, things like that. So people like that. Yeah, that's one thing. We start with our a lot of times volunteers, and then we're going to randomize them. We start with our volunteers. We randomly assign them to the treatment groups. So if there is a control group, I think that's a good thing to say. It doesn't always have to be a control group. You can compare two different treatments. You might have a placebo, a fake pill, a dummy treatment. You might not. You might just compare, we're going to test against the control of Tylenol, right? Tylenol is the standard treatment for this type of headache, but we got this new drug we want to try and see if it does better. Or you might just compare a couple of different things, but you need something to compare to. If you just study one group, like, you won't have any baseline, you won't have anything to compare to. I mean, maybe historical data, but that's, at that point, it's not really an experiment. It's more observational, because we need to keep those groups so we can actually have some control with that randomization part. So you might have just a couple of treatments. You might have lots of treatments. You can have you know lots of treatments. You can have different like there's these other terms, factors and levels. I haven't seen those come up a lot, but factors are basically different variables. So you might control like a dosage amount, but then also have another factor of exercise level, and you might have three different dosages and three different exercise levels, and so that ends up leading to like 9 combinations of treatments or something like that. I doubt they'll get into the weeds with that, but those concepts were mentioned in our book. The placebo is that dummy treatment. A lot of times it can be a fake pill, but it could be also just like a non-medical ointment, or like I think I mentioned even there's some weird like placebo surgeries and things like that where you make people think that they got it because we see this psychological effect where this placebo effect where people get better. Even if just because they think they're taking a pill, or it might just be like people get better just because time passes, right? But that placebo, specifically that dummy treatment, is for that psychological effect. All right, so then another thing you can have is double blind. You can single blind as well, but a lot of times double blind is good. It doesn't let anybody. It's this idea of you don't let people know which treatment they got if possible. So you may not let them know, oh, you got the placebo. That kind of ruins the whole point. Or they won't know which dosage level they got, and the doctor won't know which one they got. So they can just kind of unbiasedly be unbiased about their the way they respond. That doesn't lead to any response bias or any kind of recorder bias or leading questioning or anything like that. So that's the idea of blinding experiments. So yeah, I mean, I already mentioned randomization, but kind of how to do it, right? You can use all your individuals and then have certain numbers go to different things. One thing I think is actually maybe not the best way to do it, but you can kind of read through this. But actually, a lot of times the easiest way to describe these in like an AP test is the drawing slips of paper from a bag. Like if you want 20 people to be in group A, you can just put 20 A's in a bag and like 20 B's in a bag and then shuffle it up and then randomly. Like a lot of times that's easier to describe than, oh, I'll go through, I'll assign everybody a number between 1 and 40. I'll randomly select 2-digit numbers from a table of random digits. I'll ignore repeats. And any numbers outside the range of 0, 1 to 40, and then I'll select those individuals for A, and I'll do that 20 times, and then the remaining will be like it's actually sometimes easier just to describe the slips of paper. In reality, a lot of times it is easier to do that digitally, but like just for AP test purposes, I think it's often easier to describe some randomization just like with like the slips of paper in a bag type thing. Like I'll put like you can just say like group 1, I'll put 20 slips with group 1 in it. I'll put 20 slips with group 2. And they'll draw their name and that's their group, or they'll draw their slip of paper. Make sure you mix the bag, and that's their group. So not a bad idea to take the AP test that way. Easier to describe. And so then they go into block design, but I thought this was actually a good kind of summary of the randomization features. So you have control and randomization. So you control variables. You keep some variables the same. You want to make sure if you're studying plants that they get the same amount of sunlight and water and so on. So you keep those variables the same. Obviously, if you're studying plant growth or humans, you make sure you keep the amount of time the same. They all take it for the same time and they take the same amount. And they do as much the same as possible. But then randomization, so that you control for the variables you can. Randomization is the main way to control for confounding variables that might influence outcomes in some way but are not considered by the design of the study. So usually because we aren't aware of them, right? Those variables that we don't think about, we don't think to control. Randomization still kind of, that's our method of controlling for those other variables. Then there's the other one we have is block design. So block design, that's again going back to controlling for a variable we think is related and we are kind of cognizant of. So if we think genders are going to be different, we block into those groups. Right? This is not random. You don't randomly assign gender. You take your volunteers and we say, oh, I got 30 males and 50 females. Okay, within my 30 males, now I'm going to randomly assign treatments and within my females because I think there might be a difference. And so then I'm going to compare within those groups, and then we can ultimately maybe compare between the groups. But the main comparison here is like just within those groups. How do the treatments and the control work for the men, and how do they work for the women? And so you block to, and I thought this was a nice summary. You block to control for variables that you know. about, and you randomize to control for the ones you don't. And so that's the nice thing about randomization is hopefully it's keeping all things, even the ones we forgot to think about, the same. And the matched tiers design is like a very small blocking. You can do it with yourself. You can have an individual do like a before after, and so you have a number before, or they might do it two different ways. You randomize the order if you can. But you can also do just pairing two people because they could be the same height or the same race or the same age or the same whatever weight like and then those individuals all get paired up, and then you give one the treatment and one the control or the other treatment, and then you can compare those individuals. And then when you do that matched pairs design, you can think going down, that actually affects the inference you do. If it's a matched pairs, you actually treat it as a one sample t-test or t-interval, because you do the list of differences for each one, and you actually just get one list of differences. So it's like you treat it like a one sample of differences. Whereas if it's not, if they're not matched pairs and you're doing differences and you're comparing these different groups, you might end up doing a two sample t-test or two proportion, depending on what you're dealing with. And then I think that's it. So hopefully you went through rapid review. Let me know what questions you have. I'm not focusing on this multiple choice type stuff as much now, as I kind of want to focus more on free response, since that's what the AP test is going to be. But that doesn't mean, like, I can't give a free response question for every potential detail. So this is still a good way of going through this and thinking about each of the details. So let me know if you have questions, right? You've got those rapid review that have the answers right there. You've got those multiple choice questions, and the answers are a couple pages later. So the solutions to the multiple choice practice problems. You've got this boatload of free response questions you could do, right? If you're looking for more to do, this is all good. Or I don't think these questions are actually representative of what the AP test will be like. I'm trying to give you old AP questions because I think they're going to try and work that content into a couple of like multi-covering questions, and we'll have some extra time that we'll look at those as well. But you can certainly do this. This is not a bad idea. But I think probably the biggest value you could get out of this whole skim read review thing is just know where things are, remind yourself of some things. That way it comes back up quickly on the test, and then make good notes so that when it's open note, so you can go back to these things and look it up real quick. You've got this nice kind of condensed review. Make sure you know where to look. So that's all I got for today. Let me know what questions you have, any other comments, suggestions, things like that. Hope you're doing well. Hope you are staying happy. I'll talk to you soon. Bye.